Good afternoon for all the present. My name is Rodrigo Guedes dos Santos, and today I will present an evaluation of thermoeconomic diagnosis through the localized disaggregations in a refrigeration system. Thermoeconomics is a science that combines thermodynamics and economics, and this science can be split in three areas: local optimizations, operational diagnosis, and cost allocation. Diagnosis is a method to search and comprehend anomalies and quantify its consequences through the symptoms. For local optimizations and diagnosis, for instance, total disaggregations of the components of the system is generally required. It is possible to combine a model with other models in a localized physical exergy disaggregation to adequately isolate the dissipative equipment with less complexity associated, as shown in Santos 2020. This paper aims to perform a localized physical disaggregation only in dissipative components, like condenser and valve, in the thermoeconomic diagnosis in a refrigeration system. Using localized disaggregation, it is possible to identify and quantify the anomalies in the diagnosis. The diagnosis method used in this work is the full impact formula proposed by Valerio in 2004, which identifies and quantifies anomalies in each component of a thermal system compared to differential conditions. One considered as a reference or design condition, and the others one as an operational condition with the presence of anomalies or faults. The anomalies can be quantified in malfunctions or dysfunctions. The full impact equations can be written as a sum of the component malfunctions and the component dysfunctions induced by the components of the system. The physical structures. The physical structures used in this work is a refrigeration system, and 5 different anomalies are similar in the system, and their influence of the consumptions of additional resources are analyzed by the full impact formula. Anomaly 1 is the reduction of 5% points in the isentropic efficiency of the compressors, and anomaly 2 is the 5% decrease in the fluid pressure during the passage of the fluid through the condenser. Anomaly 3 is the extra 5 reductions in the fluid pressures during the thermostatic valve. Anomaly 4 is the 5 pressure loss during fluid flow through the evaporation, and anomaly 5 is the combination of anomaly 1 to 4. In this table you can see the reference states and the other parameters for the anomalies. These 3 figures shows the product diagrams of the refrigeration system using the E-model, which uses total exergy flows as the thermodynamic magnitude to define the product structures with localized exergy disaggregation. The E-model is being used in all components except in the condenser and the valve, where the UFS model must be used. E and UFS model is the name of the product structures. The complexity is reduced in this case. The first figure in the right, the E-model is being used in all components except in the condenser, where the H and S model should be used, and valve, where the thermoeconomic or thermoeconomic asterisk model can be used. It is worth mentioning that the product diagrams using thermoeconomic or thermoeconomic asterisk is the same. The difference between the figures on the right is the kind of disaggregation used in the valve. In this case, it is used UFS model. These combinations, E and UFS, E, H and S and UFS, E, H and S thermical and mechanical, and E, H and S thermical and mechanical asterisk, are called localized physical exergy disaggregation, which was proposed by Santos in 2020. The results about anomaly 1. All methodologies proposed are capable to identify the fault accompanying anomaly 1. The figure shows the highest value association with the compression. It is worth mentioning that anomaly 1 restricts the inefficiency only to compressor, mostly because it is the input of the system resorts, not affecting the other equipment. It also observes small values of dysfunctions in all methodologies due to the difference in thermodynamic states of the fluid downstream of the compressor. About in anomaly 2, in this case it is not possible to identify the subsystem with malfunctions. Although in these anomalies the condenser has a reduction expressions values, the highest malfunctions value is associated with the evaporators. Only for this analysis the evaporator is wrongly identified as a defections component due to the presence of faults in large quantities. It is important to highlight that the fictions units induce anomalies in other real components, although they do not have any dysfunctions or malfunctions in them. Anomaly 3. Although the results shows a value of malfunction associated with the valve, the highest value of the malfunctions can be observed with the evaporations. One more time, it is not possible to identify correctly the subsystem with the malfunctions, and the fictions units also induce anomalies in other real components. In this case, for all models, the compressors do not have any dysfunctions or malfunctions, and the evaporation case dysfunctions in all other subsystems. About anomaly 4. For this anomaly, this research presents current results, since all methodologies proposed are capable to identify anomaly 4, and the evaporator shows the highest value of malfunctions. In the other components, the models present the same trend, including the fictions units, which also induce anomalies in other real components, except the evaporation. Anomaly 5 is the most likely scenario to occur in a real diagnosis analysis, where faults could be present randomly in every component of the system. It is observed that the evaporation has the highest malfunctions value, and it also induces a large number of dysfunctions in other components, causing a great additional fuel impact. Although the compressor shows all malfunctions, there is no dysfunctions associations with them. Negative values of dysfunctions are found in the valve, in the A, H and S thermal and mechanical model. It happens due to a component product's reductions when compared to the reference state. The conclusions. For anomalies 1 and 4, all methodologies proposed are capable to identify the malfunctions of compressors and evaporator. The results due to anomalies 2 and 3 show that it is not possible to identify the subsystem with malfunctions. The fictions units induce anomalies in other real components, although they don't have any dysfunctions or malfunctions in them. Negative values of dysfunctions are found in the valve in the E, H and S thermal and mechanical model. The EUFS and EH and S UFS model presents the same results for all anomalies and similar to other models. Any models that use a correct localized physical disaggregations are able to isolate and treat the condenser and the valve and can be used for diagnosis analysis. Thermoeconomic diagnosis with localized physical excessive disaggregations allied to a product structure that does not present fictitious elements could be promising. I want to say thank you for the opportunity, and if there is any question, I am here to try to answer. Good afternoon.